Welcome back, everybody. We are to the last chapter, chapter 11. And today we're going to talk about goodness of fit. Let's write that out. A goodness of fit model is used to test the hypothesis that an observed frequency distribution fits some claims distribution. And so we're going to go ahead and conduct that. The requirements are that the data has to be randomly selected. The sample data consists of frequency counts for each of the different categories. And for each category, the expected frequency is at least 5. If it's below 5, then it gets a little sketchy, and this particular test doesn't work so well. Our null and alternative hypotheses. Our null hypothesis is that the frequency counts agree with the claimed distribution. And the alternative is that the frequency counts do not agree with the claimed distribution. Which brings us to our test statistic. So this is chi-squared. And this is going to be, and let me define these for us. O are the degrees of, this is k minus 1, are the degrees of freedom. The goodness of fit hypothesis tests are always right-tailed. We'll need to keep that in mind as we go through this. The O represents the observed frequency of an outcome. So the O is for the observed. Excuse me. E is the expected outcome, what we would expect to happen if everything was the same, meaning the counts agree. K, which I've already used, represents the number of different categories, and N represents the number of trials. This is of the observed sample values. So we have a couple of examples. We're going to start with this one here. Records of randomly selected births were obtained and categorized according to the day of the week that they occurred. Because babies are unfamiliar with our scheduled weekdays, it is reasonable claim is that births occur on different days with different frequencies. Use a 0.01 significance level to test that claim. Now, before we get going on this, I want to, first of all, the null hypothesis is that births occur on different days with equal frequency. The alternative is that they don't. Meaning some days is more often than others. And let's put our, this is going to be an F distribution, a chi-squared distribution, pardon me. The graphs look very similar. And in this case, we have a 0.01 significance level. And we need to get our test statistics so that we can get our p-value. And then we'll compare our p-value to our alpha here. So to get our test statistic, I've set up this table. And E in this case is going to be it's going to be 77 plus 110 plus 124 plus 122 plus 120 plus 123 plus 97 divided by 7, because there's 7 days in a week. This is our expected value for all of them. And what I'm going to do is I'm going to store that off as A. So this is 110.4, 110.4, 110.4, 110.4, 10.4, 10.4, 10.4, because we are expecting there to be about, if there's this many births in 1 week, we expect there to be about the same amount on each day. Now the O minus E, I'm just going to do this first one here, and then I'll show you the cheat way to do it. If your calculator has it. Not all calculators are going to have the cheat way to do this. So some of the older models will not. So this is O. So O minus E is 77 minus A. Oop, plus 77 minus A, negative 33.4. I'm going to square that, squared. And I'm going to divide that by E, which I saved off as A. So divide by A. And what I would do is I would do the same thing for all these processes and then add these up. Because that's the formula right here for a test statistic. So if you don't have a goodness of fit button, like I'm about to show you, and by the way, in my calculator, this is list 3, this is list 4. I'm going to show you how to find the magical button if your calculator has it. So stat tests, we go towards the bottom, and here is our chi-squared goodness of fit test. As I mentioned, I have my data in slot 3 and 4, so 3 and 4. Degrees of freedom is going to be 6 because it's n minus 1, or k minus 1, pardon me, and k in this case is 7. And this is going to calculate for me my test statistic. So chi-squared is 16.895. And the p-value that it gives me is here, very small, actually. .0.09676, which is definitely less than 0.01. Now, let's say that you had to actually do it manually like this, and you got your test statistic. The way we would do that to figure out what the p-value is I would go to, let me write it out, chi-squared CDF, and that would be 16.895 to a big number, and then the degrees of freedom, which in this case is the 6. Let's see what we get. Distribution, chi-squared CDF, 16.895, and there is our p-value. So you can do it either way, manually or with a calculator. Manually, it's not hard, it just takes a little bit more. I would recommend you use different memories as you go through these to save them off. Remember, you have lots of memories, A, B, C, all the way through Z and so on. So all the way through Z, you even have a theta that you can use. All right, so what's our conclusion? Well, since our p-value is less than our alpha, we are going to reject the null hypothesis. So there is sufficient evidence to support claim that, and I'm running out of room here, that births occur on different days with the same frequency. We have it. Next up, example 2. A police department released the numbers of calls for the different days of the week during the month of October, as shown in the table below. Use a 0.01 significance level to test the claim that the different days of the week have different frequencies of police calls. So once again, our null hypothesis. So I'll just put same frequency. There's the alternative, is that they're different frequency. Meaning more calls are made on a Thursday than a Saturday or something like that, is what we're trying to check. Or are they all equal? All right, so here's the, this is part A here. Calculate the test statistic. I have put this into list 1 and this one into list 2 into my calculator. You may need to take a minute and pause the video to do that. So part B, I'm going to use the faster way. You may, if you can't do the faster way, you'll have to set up a table like this again to help you organize your thoughts. And let's make sure my table is what I said that it was. This is list 1. And list 2 is what I did was I added up 157, 201, and so on, and divided it by 7. And I came up with 206.14. Let's go ahead and do that real quick, just to show you. 157 plus 201 plus 227 plus 241 plus 173 plus 209 plus 235. And then divide that by 7. And this I stored off as, oops. Show you another trick here. Hit there, and now I can store that as a, there we go. So that is going to be my expected, 206.1, 206.1, and so on. And so what I've done is you can see 26, and I actually stored off all that memory to do that and put in A. So list 1 is here, 157, 201, and so on. And then here's my expected. So again, these are my O's and these are my E's. So let's run the test again. And let's also draw it out a little. And this was 0.01 again. We could figure out what that is as far as a critical value, but I'm just going to go by the p-value in this case once we do it. So let's get a test statistic and the p-value. So we're going to go to tests. We're going to go to goodness of fit, if you have it. And I'm in list 1 and list 2. Degrees of freedom 6 again. Again, these are 7 days in a week. And calculate. So we got chi-squared is about 29. Ooh, that's not good. 0.2557. And part C is the p-value. Is about, now I want to show you, it looks like it's 5, but it's not. It's times 10 to the -5th. So it's actually going to be 0.1234544, which is clearly way less than the 0.01. Once again, we are going to reject the null hypothesis. So there is sufficient evidence to support a claim that different days have different number of police calls. There you have it. All right, so here are the conclusions.